Hi everyone, my name is Quentin Adam. I created a company called Clever Cloud. It's working there, but I'm not here to talk about Clever Cloud today. I'm here to talk about the Mac Air. I don't know if you have heard of Mac Air before, but Mac Air is an emergency ventilator built for the answer to the crisis of COVID. So let me explain you what is the story. On March 17, I understand that there will be a problem about the numbers on ventilator everywhere in the world. So with a bunch of friends, the people of CRISP, Baptiste Jamin, Valérian Saliou, the people of the Nantes Hospital, Pierre-Antoine Gouraud, and some people working with me, Emmanuel Feller, we understand that we have a problem. And this problem was, okay, we need some more ventilator. We don't know how to build a ventilator, but what we know is the world needs more ventilator, and to be sure that to have more ventilator, the best solution was open source. So we decided to launch a project, made a few video, you can find it on YouTube. The first beginning of the Mac Air with a prototype, which is this one. So this is the first prototype of the Mac Air with some crappy electronics. So we're starting to work. And we're starting to interview with some physician needing the Mac Air needing some ventilators. So we're starting to have a few people answering our question about what is a ventilator and why they need it and everything. And during this process, we find more and more people interested in the idea. So we structure the team to be able to answer the question. The first question was how to build a ventilator. For this, we need the answer to what is a ventilator. For this, we have an interview with about 10 people working from anesthesia and reanimation. And the answer to the question of what is the kind of ventilator you need in case of crisis of COVID. The second question is how to build it. To build it, we need some people from mechanical to electronical to software people, and everyone working together to build something which is delivering the capacity and error of people will need in this case of COVID. The third question was how to make sure that a doctor can apply it to a patient, because the regulation on the world of medical device is very important, and you cannot just create something and put it on a patient and that's it. And we learn very interesting stuff on the way, which is, in the case of a ventilator of a medical device, what is the certification is not the plan, the source code of the medical device, but the industrial process to build the medical device. And it's very complicated to have the certification medical stuff. So we were looking for people able to help us. So we create a community and we put everything on GitHub. Every night I do a quick recap of the day on YouTube. And YouTube, we have this video explaining what we do and what we need. And on 5 days after we're starting to work, I have a phone call from someone I didn't know before called Eric Renneker. He is leading a company called Diabeloop. And he is, and his partner in crime, Marc Julien, decided to commit to help us to work on this. And Diabeloop is working on the eye-powered pancreas, and it's a medical device. So what Eric and Marc make is, okay, build the ventilator, we will build the certification for the ventilator. And as the certification is the industrial process to build the ventilator, we need to answer the fourth question. And the first question was how to build a lot of ventilator. Because building one ventilator and be able to put a patient on is not enough to answer the crisis. But the real question is how to build a lot of ventilator for cheap and put it on patient. Building that, we have made more and more people coming to us, like Pierre Papin, Sherin Kamel, Vincent Lequinf, and a lot of companies like paesi, Tronico, Renault, Seb. A lot of companies help us do the job. And we have in 2 weeks, about 200 people working a lot on this project to make sure it's happen and work very well. So it's important to understand that the whole process have been very simple. Few people in the lab because it's COVID and we don't want people to get infected. Everyone is working online. 2 check-in calls per day, and have very, very precise team. So we have one team working on certification and documentation, and there are multiple teams inside, like biocompatibility, software certification, hardware certification, and so on. It's about 60 people. We have a team working on valves, and then multiple teams, electronics, and then multiple teams, mechanics, and then multiple teams, and software, multiple teams. And then we have the people linking with the authority and all the institution. And we have all the people working on, several layer of people working like that, working very well together to make the stuff happen. So 2 check-in video calls and 1 on the night YouTube recap to make sure everyone keep in the loop. All the source code is on GitHub, and the discussion and the working is happening on Slack. So keep working on. We have help from many people. So the French army helped us, giving us some funds. Something we call CEA in France, which is the Center for Atomic Energy. It's part of research, part of army, and they're working of basically the atomic bomb, but many other stuff. And they help us a lot on this process. So at some point, we take all the guys and we put everyone on the CEA in Grenoble and working together at finishing the system. And then put it on the regulation. What's going to be interesting there is I can show you what we have made with them and what we have done on this. So basically, here is one of the machine. I don't know if you have here. That's what I do. Here is stuff we have built. So this is the first. I can convince the stuff to just put on. So here is the maker, and if you look at this, it's a very simple system. Basically, it's a system with 2 valves and a blower and electronics, battery, and so on. Why it's so simple? Because the big idea of the maker was, okay, let's build everything around the software, then build the hardware around it. So it's not a machine where we put some software inside. It's a software we dress with some hardware. It's a very different case. And it's linked to the open source vision of the stuff. Because if you think about it, medical hardware is very expensive. It's something people don't know how it works. It's a black box. And they cannot reproduce it. And it was really the big issue on the COVID was you don't know how to reproduce it. So what we have done is build some stuff that people can reproduce on themselves, build a new industrial process to produce it, and then having people using it when they want. So if you look at what we have done there, it's a very simple machine, but it's a machine where actually works. If I take a fifth long, I can have the machine. Calibration has been fake because I plugged the patient. So the machine is calibrating itself, and if we plug it, we have the machine actually be able to work. and we can start the stuff, and the patient start breathing. I don't know if you look at this. Patient start breathing. What's interesting here is this is a fully parameterable stuff. So I can have a lower plateau and the lower pad. The number per minute is slowing down. And then I stabilize the patient. And the patient is not stable. What is important here is when you build something like that, you need to be sure that everything will be working. So it's not working on the Linux or anything else. It's working directly on the microchip. And the microchip is working on what we call ST microelectronics. So in this stuff is a very small stuff, and what's interesting us is there. All the code is inside it and run and called what we call the servo loop. The servo loop is the ability to I can maybe unplug it to be sure that okay. What is interesting is the servo loop is able to maintain a level of pressure behind the time. It's a very simple design, but making this design viable, we are able to reach the good level of pressure and build an iterative model on top of that. So basically, this one made in 3 weeks, and in 3 weeks we put it on a pig, and we're starting what we call the preclinical trial, which is a certain level of test where the whole machine has to pass to be able to be plugged to someone. Preclinical tests have 2 different aspects. What we call technical test, which is a fake lung, but not this one. A very big one called ISL 5000, which is a very expensive piece of hardware which actually reproduces the lung and which is very precise. And on the other side, the biological test, where we put some animal like pig on top of the ventilator and have the ability to see if it's working very well or it's going down. So we have all the clinical trial and going to certify this version. And then start speaking with industrial on the side. I forward you that basically all the bureaucracy in all countries, being bureaucracy on all countries, we have waited a lot of authorization to have clinical trial. But on the same side, we were working iteratively on new version of the machine. What is interesting here is this one is a machine who cost about 1,200 euros to build. And it's compared to machines that cost 15 to 20,000 euros. So when we build this, we actually give to the people something very cheap to access, and we be able in the CEA to working on industrial building of this. So the first shot was about 60 machine works, and not built by the team who conceive us, but with all those people, which is really an industrialization. Because like I said before, what is important is to build the machine, to have the plan, have the certification, and have a process to produce it in a large volume. So we're starting with this case, and we're starting to ramp up this and put all the certification in line, and then we wait for the bureaucracy. And the bureaucracy have been waited for 2 months. And while the bureaucracy was doing some bureaucratic stuff, we have made another maker. And do is maybe unplug this totally. So while we are working on this, what we have done is building another maker. And the maker I want to show to you is this one, is here. This is a new Maker V3. The Maker V3, this one, is a little bit more complex and way more precise. Because basically, this machine is about to achieve some very good volume of pressure on everything. So the change is now we have a very big, great screen, and we have changed many things inside. So first, you look at it. Electronics. So I can show you the same electronics here. So electronics is in two parts. The two parts are this one. This is where the electronics is safe, and there you will have the microchip you have seen before on the small cards, but no, directly on the card. Here you have the communication with LoRa and Wi-Fi, and here you have the Raspberry. Here is the safe part. This part of the electronics cannot break, and all the code is directly on this. And this is the electronics who actually show graph and many cool usage, but it can break. It will never change the function of this. So what's interesting here is this, and we have also this. So we change the way we do the valves to have something more powerful, more stable, more credible. So if I show you the stuff, is this one. So we just put the pipe here, and giving the inclination, the rotation, it will be able to just pinch the valves and block the airstream and that. So this is what we have changed. Electronics is new. Many other things are new. And just 1 month after we have built that, this is a really good advance because we have been able for nearly the same machine to add a lot of cool feature inside it. So if we start, once again, we are breathing. And now we see the respiration happening. But what is interesting on this version of the software is we are able to change the longer of the inspiration over the expiration here, which can be different. So we can be more and more able to link with more patients. We can change the plateau, the expiratory, the peak, and the number of respiration like everyone. Now we have the volume of air we put inside the patient, which is another interesting feature, but more. Now we can have a patient where the sedation is not working very well. Just explain you. When you are on a ventilator, you're heavily sedated with Cura. So you cannot actually breathe by yourself. The ventilator is doing it for you. But if you have a problem and starting to breathe, there is a problem because you're starting to breathe and the ventilator is starting to breathe for you, and there is a problem with that. This is a conflict, and people have a problem of, air and CO2 and everything. With this machine, what we have been able to do is detect where the people want to breathe and actually have the ability to detect it and following it. Like, for example, if I'm starting to breathe, like you see, I don't activate it. Okay. So now the trigger is activated. So if I'm starting to breathe, the machine is actually following me and amplify. So that's allow to have some people with their own way to inspirate, or maybe people who want to expirate, which will break the lungs, and we will inflate this for them. So basically, with that, we have the ability to help people in the countries where sedation can be bad, for example, because they have lack of money or stuff like that, and working very well. And as you see, I never flag the machine because there is huge battery inside it. So what is interesting here is all this new feature is only there because the software can do it. And that's why it's important for me to talk about what we can do on the open source on hardware is. If you think about it, every people who help us to put this kind of feature inside the ventilator are just people just wanted to help. And in any ventilator, it's not possible, because if you want to have something new in the ventilator, you need to work on the company building the ventilator to make something new. With the maker, everyone who has an idea of a new algorithm to improve the breath can basically help us. Everyone who has an idea to have a cheaper or a better solution to manage the airflow can just ping us. And that's why I think that today, working on open source industry, open device, something where everyone can contribute and help, is a very interesting way to do medical stuff. Because all of what we have done, just the 3 weeks working on a machine and to be able to plug it on an animal and works well, show that open source and collaborative working is better than just keep it closed. If you look at this from a software perspective, in the past 30 years, there have been a fight between closed source and open source. And right now, everyone is knowing that open source have win the stuff. And what we have done with the Maker is basically something that everyone can be able to do. It's just having something that it's open source and open to the collaboration for everyone. So I know there is just a few minutes left for this question, and maybe it can be interesting if you have some question to ask about how we have made. Many of the plans on how it works are available on YouTube and GitHub, and can show you how it works. And there is a huge website also with everything. So if you need, if you have any information you need about how to build an open source ventilator and open source community out of nothing in just a few days, now it's the time to ask. Yes, there are very lower cost. So the question is, do this device have a lower cost than traditional machinery? Yeah. So traditional machinery on ventilator is a pretty large possible of price. So you will have it from 15,000 euros to 80,000 euros, depending on the feature and the quality of the ventilation. For this kind of COVID-related disease, the thing is, you don't plug the patient for just a few hours, but for days or weeks on the machine. So it has to be very precise on the level of pressure and volume it puts inside the patient, because if you don't do that, the problem will be that you will basically break the lungs of the patient, and the patient will sometimes have a problem for breathing for the rest of his life. So you need to be very precise. So it's more 40 or 30 at the lower cost of the machinery. The hardware needed for building this one is around 3,000 euros. So basically, we're speaking about 10% of traditional price. Does this device will replace traditional machinery? It depends on everything. For the part where we are good, which is long-term reanimation, I think this is one of the good device and can replace the machinery when we have done those things with the noise, because it's a little bit noisy for the moment. But we have few samples without the noise and with a few good other stuff working on. But what is interesting with this is, what I hope is, when an hospital can be able to have open hardware everywhere, we will be able to change the world. Because if you think about that, the machine here is able to send the data of how it works, all the breathing, all the incident, everything about the patient, directly live on an open protocol. So people can actually analyze that. None other of the old hospital machinery is able to do that. All the data is locked. All the data is black boxed. And I think that if we go on open hardware on the hospital, we can change the world because first, the data will be available. Then the data will be synchronized between all the device. If you have a device, who takes the saturation on the blood, and this one linked together to the patient, they don't know each other, and the data of the two are not linked and not, channelized to something able to do the diagnostic together. You have to be on the same room and look at the two screens. It's the only way to synchronize the data. If you think about that, it's totally crazy. When this sci-fi stuff that where people enter the stuff and say, computer, what is the diagnostic? To be fair, that today we know how to diagnose with the data, but we don't have the data. Why? Not because it's complicated to synchronize data. You all know Sonos or AirPlay stuff. We know how to synchronize data. We are not able to synchronize the data just because it's proprietary software. And I think that if together we can work on new computer, it can be the way to produce better machinery and better stuff together. So yes, I hope open device on medical can be replaced traditional medical device. I don't know what is right on the chat. If you can, do you have any other question? Okay, thank you very much. I see that the live I finished question. So thank you very much. Just follow Maker on Twitter, and we will be able to give you more insight about what we do. And I hope we will see you each other and see you soon. So thank you very much. Voilà.